Babylonian engineers and surveyors found ingenious ways of accessing water and channeling it to the crop fields. Yet again, they used mathematics to come up with solutions. The Orontes Valley in Syria is still an agricultural hub, and the old methods of irrigation are being exploited today just as they were thousands of years ago. Many of the problems in Babylonian mathematics are concerned with measuring land, and it's here we see for the first time the use of quadratic equations, one of the greatest legacies of Babylonian mathematics.
Quadratic equations involve things where the unknown quantity you're trying to identify is multiplied by itself. We call this squaring because it gives the area of a square. And it's in the context of calculating the area of land that these quadratic equations naturally arise.
Here's a typical problem. If a field has an area of 55 units, and one side is 6 units longer than the other, how long is the shorter side? The Babylonian solution was to reconfigure the field as a square. Cut 3 units off the end, and move this round. Now, there's a 3x3 piece missing, so let's add this in. The area of the field has increased by 9 units. This makes the new area 64, so the size of the square are 8 units. The problem solver knows that they've added 3 to this side, so the original length must be 5. It may not look like it, but this is one of the first quadratic equations in history.
In modern mathematics, I would use the symbolic language of algebra to solve this problem. The amazing feat of the Babylonians is that they were using these geometric games to find the value, without any recourse to symbols or formulas. The Babylonians were enjoying problem solving for its own sake. They were falling in love with mathematics.
The Babylonians' fascination with numbers soon found a place in their leisure time too. They were avid game players. The Babylonians and their descendants have been playing a version of backgammon for over 5,000 years.
So the Babylonians played board games, from very posh board games in royal tombs, to little bits of board games found in schools, to board games scratched on the entrances of palaces, so that the guardsmen must have played at times when they were bored. And they used dice to move their counters round. People who played games were using numbers in their leisure time to try and outwit their opponent, doing mental arithmetic very fast. And so they were calculating in their leisure time without even thinking about it as being mathematical hard work.
Now's my chance.
I hadn't played backgammon for ages, but I reckon my maths would be good enough to give me a fighting chance.
Okay.
So it's up to you.
So 6, and I need to move something, so...
The point is up to you.
But it wasn't as easy as I thought.
Okay.
Ah, what the hell is that?
Yeah, this is...
This is 1, this is 2. Now you're in trouble.
So I can't move anything, can I? I can't move these anyway.
You cannot move these, you're gonna
I just
play
gotta...
on
Oh, gosh.
Exactly. There you go.
You seem to be...
Right? 3 and 4, so...
Just like the ancient Babylonians, my opponents were masters of tactical mathematics.
Yeah. Put it there.
Here you
Alright,
go.
good game.
The Babylonians are recognized as one of the first cultures to use symmetrical mathematical shapes to make dice. But there is more heated debate about whether they might also have been the first to discover the secrets of another important shape, the right-angled triangle. We've already seen how the Egyptians used a 3-4-5 right-angled triangle. But what the Babylonians knew about this shape, and others like it, is much more sophisticated. This is the most famous and controversial ancient tablet we have. It's called Plimpton 322. Many mathematicians are convinced it shows the Babylonians could well have known the principle regarding right-angled triangles, that the square on the diagonal is the sum of the squares on the sides, and known it centuries before the Greeks claimed it.
This is a copy of the arguably most famous Babylonian tablet, which is Plimpton 322. And these numbers here reflect the width or height of a triangle, this being the diagonal. The other side would be over here, and the square of this column plus the square of the number in this column equals the square of the diagonal. They are arranged in an order of steadily decreasing angle on a very uniform basis, showing that somebody had a lot of understanding of how the numbers fit together.
Here were 15 perfect Pythagorean triangles, all of whose sides had whole number lengths. It's tempting to think that the Babylonians were the first custodians of Pythagoras' theorem, and it's a conclusion that generations of historians have been seduced by.
But there could be a much simpler explanation for the sets of three numbers which fulfill Pythagoras' theorem.
It's not a systematic explanation of Pythagorean triples. It's simply a mathematics teacher doing some quite complicated calculations, but in order to produce some very simple numbers in order to set his students problems about right-angled triangles. And in that sense, it's about Pythagorean triples, only incidentally.
The most valuable clues to what they understood could lie elsewhere. This small school exercise tablet is nearly 4,000 years old and reveals just what the Babylonians did know about right-angled triangles. It uses the principle of Pythagoras' theorem to find the value of an astounding new number.
Drawn along the diagonal is a really very good approximation to the square root of 2. And so that shows us that it was known and used in school environments. Now, why is this important? It's because the square root of 2 is what we now call an irrational number. That is, if we write it out in decimals or even in sexagesimal places, it doesn't end. The numbers go on forever after the decimal point.
The implications of this calculation are far-reaching. Firstly, it means the Babylonians knew something of Pythagoras' theorem 1,000 years before Pythagoras. Secondly, the fact that they can calculate this number to an accuracy of 4 decimal places shows an amazing arithmetic facility, as well as a passion for mathematical detail.
The Babylonians' mathematical dexterity was astounding, and for nearly 2,000 years they spearheaded intellectual progress in the ancient world. But when their imperial power began to wane, so did their intellectual vigour. By 330 BC, the Greeks had advanced their imperial reach into old Mesopotamia. This is Palmyra in central Syria, a once great city built by the Greeks. The mathematical expertise needed to build structures with such geometric perfection is impressive. Just like the Babylonians before them, the Greeks were passionate about mathematics.
The Greeks were clever colonists. They took the best from the civilizations they invaded to advance their own power and influence. But they were soon making contributions themselves. In my opinion, their greatest innovation was to do with a shift in the mind. What they initiated would influence humanity for centuries. They gave us the power of proof.
Somehow they decided that they had to have a deductive system for their mathematics. And the typical deductive system was to begin with certain axioms which you assume are true. It's as if you assume a certain theorem is true without proving it. And then using logical methods and very careful steps, from these axioms you prove theorems. And then from those theorems you prove more theorems. And it just snowballs that way.
Proof is what gives mathematics its strength. It's the power of proof, which means that the discoveries of the Greeks are as true today as they were 2,000 years ago. I needed to head west into the heart of the old Greek Empire to learn more. For me, Greek mathematics has always been heroic and romantic. I'm on my way to Samos, less than a mile from the Turkish coast. This place has become synonymous with the birth of Greek mathematics, and it's down to the legend of one man.
His name is Pythagoras. The legends that surround his life and work have contributed to the celebrity status he has gained over the last 2,000 years. He's credited, rightly or wrongly, with beginning the transformation from mathematics as a tool for accounting to the analytic subject we recognise today.
Pythagoras is a controversial figure. Because he left no mathematical writings, many have questioned whether he indeed solved any of the theorems attributed to him. He founded a school in Samos in the 6th century BC, but his teachings were considered suspect, and the Pythagoreans a bizarre sect.
There is good evidence that there were schools of Pythagoreans. They may have looked more like sects than what we associate with philosophical schools, because they didn't just share knowledge, they also shared a way of life. They may have been communal living, and they all seem to have been involved in the politics of their cities. One feature that makes them unusual in the ancient world is that they included women.
But Pythagoras is synonymous with understanding something that eluded the Egyptians and the Babylonians: the properties of right-angled triangles. What's known as Pythagoras' theorem states that if you take any right-angled triangle, build squares on all the sides, then the area of the largest square is equal to the sum of the squares on the two smaller sides. It's at this point for me that mathematics is born and a gulf opens up between the other sciences. And the proof is as simple as it is devastating in its implications. Place 4 copies of the right-angled triangle on top of this surface. The square that you now see has sides equal to the hypotenuse of the triangle. By sliding these triangles around, we see how we can break the area of the large square up into the sum of two smaller squares, whose sides are given by the two short sides of the triangle. In other words, the square on the hypotenuse is equal to the sum of the squares on the other sides. Pythagoras' theorem.